Okay, so last time we made a tiny little mistake. So this theorem in which we are going to use the axiom of choice, we don't want to talk about locally small categories, but rather we just want to talk about small categories. So just make that change and then we can start with the proof. So let me remind you what the theorem is. Given small categories C and D, a functor is a part of an equivalence, which means there exists the data, like complete data of equivalence of categories, if and only if that functor itself has some properties. Yeah, the functor is fully faithful and essentially surjective on objects. So what is the meaning of fully faithful? That on home sets, the functor induces a bijection, and essentially surjective on objects means that every object in the target category is isomorphic to something in the image. So basically the image of this functor intersects every isomorphism class in the target category. Okay, so all these definitions are written and we are going to prove this theorem now. So let me start with the proof. One side is very simple. Yeah, so we are going to prove this side. Suppose f, g, eta, epsilon are the data of an equivalence between C and D. Suppose this data is given. Now we have to show that the functor is fully faithful and essentially surjective, the functor f. Yeah, if you want, I can write some diagrams. I mean, they are just here. So we need to show. Let us first show. Yeah, we will. F is essentially surjective. Yeah, this is the thing we are trying to show. How do we show that? F is isomorphic to an object in the image of F. Sorry, every object. So given some D in D, which object is isomorphic to D and which belongs to the image of F? From this basic data, can you tell me? Like f, g, eta and epsilon. Where is the map eta from? One C, identity functor on category C to GF. Okay, so this is not going to help. Yeah, because it only talks about objects in C. What about epsilon? Objects in D, yes. So what do we have? So epsilon, at which object we are talking about? Epsilon sub D is a map from FGD to D. Yeah. Is, what can you say about this particular arrow? This arrow is an, okay, if you have forgotten, let me quickly go up. See, we have said that there exists a G such that these are isomorphisms, natural isomorphisms. And if you remember, what did we say about natural isomorphisms? There was a remark earlier, if you remember. Let me go back to an appropriate. Yes. So look at this exercise. If alpha is a morphism, say that show that alpha is an isomorphism if and only if each component is an isomorphism. So if you remember this, then what can you say about epsilon sub D? That's an isomorphism. Yes, is an isomorphism. So therefore, FGD is isomorphic to D. So essential surjectivity is done. Yeah. I mean, I'm writing here since epsilon is a natural isomorphism. Okay, so this is quite simple. Then we have to show that F is faithful. So F is faithful. How do we show that? We have to show that if there are two different morphisms, between two objects, C1 and C2, two parallel morphisms whose images are the same, then those two morphisms are also the same, images under F. But we are not going to do that complicated of a process. We don't need to. Yeah? We just have to see how a particular morphism is itself determined by its image under F. Okay? So, given F from C1 to C2, notice that, yeah, we have a diagram, yeah, C1 to GF C1, yeah, then there is C2 to GF C2, and here is F and here is GFF. Okay. So, what are the horizontal maps here? What's the first one? C1 to GF C1? That's eta. That's eta sub C1. Yeah, it's the C1th component of eta, and this is the map eta sub C2. Note that this commutes, which I am just going to write by drawing an arrow inside. This commutes, and eta sub C1 and eta sub C2, yeah, are both isomorphisms. Same argument, because eta is a natural isomorphism. So, F is equal to, what can we say? F is actually eta C2 inverse composed with GFF. I am purposely writing G of FF composed with eta C1 is determined, I mean uniquely determined by F, by FF. You understand this? It's uniquely determined because it can be obtained as a composition which involves two isomorphisms obviously and one FF. So it depends on FF. If there was some other morphism F prime, then it will be FF prime, and FF are same, then F is equal to F prime. You can get from this identity. Right? So that's why we have concluded that F is faithful. Yeah? So therefore F is faithful. Any questions? Okay, then let's go to the third part. F is full. Whatever we did for F, yeah, F is not spatial. Equivalence of categories means both categories are at the same level, they have same properties. So if F is a part of an equivalence, then similarly G is also a part of an equivalence, right? So for that reason, like an argument similar to above, to the above shows that G is faithful. Okay, so G is faithful. You can conclude that F is full from the fact that G is faithful. Okay, let's see how. Yeah. So let FC1 to FC2, let there be a map, be a morphism. Okay, if this is a morphism, what do you need to show? That this particular little g lies in the image of capital F. But what morphism can that be? F of what? You have to figure out that morphism. You have some data right now, and your idea is that you have to use something similar to what you had in 2. The commutative diagram that was in 2. Similar diagram can be utilized, and you had to construct a morphism and claim, because G is faithful, that this has to be the only morphism which satisfies this property. It can't be anything else. Okay, I will give you the solution. Then I am saying you do this. GFC1, you have eta C1. Now what morphism will I take here? GFC1 to GFC2, which morphism will I take? The only thing I know. GG, not GF. There is no capital F, right? GG. So this is the morphism. Then the composition, then call this composition in the diagram as F. Okay, because this is a map starting from C1 and it's ending at C2. So that's your F. What can you say about this F? If you put, I mean eta C2 inverse, I can change its direction, then even if I put, I'm going to write it in a different thing, even if I put GFF over here, then also this diagram commutes. I'm putting this F over here, that's our name. So with F, there are two different morphisms, GG and GFF, such that this diagram commutes. But G is faithful. Therefore, yes. Okay. Now, since the diagram commutes, with either GG or GFF on the RHS, vertical right side, by faithfulness of G, FF is equal to G. So what did we show? That capital F is full. Therefore capital F is full. This is the beauty of category theory. Everything either works or it doesn't. Okay, I am going to take a new page now to prove the converse part. So the converse part says that suppose f from C to D is fully faithful and essentially surjective on objects. Now we have to construct some G. Yeah, we need to construct a functor G, and on top of that we also need to construct the natural isomorphisms eta and epsilon. Yeah, so there is a lot to construct. The only thing that we know is the axiom of choice. Okay, so by essential surjectivity, and the axiom of choice, what can we say? For any D in objects of D, choose some object of category C, some object, but I am going to call it GD of C such that FGD is isomorphic to. Okay, where are we using the axiom of choice here? Choosing, we are making choices, and one choice for each object of category D. Yeah, so we are making potentially infinitely many choices at the same time. That's why the axiom of choice is important over here. Okay, so choose some object GD of C such that this happens. Okay, our functor is not yet defined. We have just defined the object to object assignment. We still have to do a morphism to morphism assignment. Okay, how do we do that? So for G, little g from D to D dash in D, what can we do? Consider, okay, so maybe this is isomorphic. In that we should label the isomorphism itself. Yeah, label this isomorphism as epsilon sub D. Yeah, this will help us. So now that we have this diagram, we are going to use the same technique as in the proof of the converse. Yeah, consider this particular composition. We want to define something from GD to GD dash, correct. So we have some morphism from FGD to D, we have something from D to D dash, and we have something from FGD dash to D dash, which is epsilon D dash inverse. Sorry, this is epsilon D dash. There is no inverse over here. And maybe I should write the inverse by changing the direction. Epsilon D dash inverse. This is G and this is epsilon sub D. Consider the composition. What can you say about this composition? Yeah, sorry? No, we first have to define something. Before attempting to prove anything, we have to first define something. So consider this composition and what will you call it? FGG? But we have to define GG. What is GG? F is full and faithful, correct?
So for FGD to FGD dash, from this we have a morphism from GD to GD.
Very good, very good. Okay, consider this composition. Now since F is fully faithful, yeah, let GG from GD to GD dash be the unique morphism such that FGG makes the diagram commute. Yes, this is possible. So FGG, if you put here, then this diagram should commute. And there can be exactly one such thing. So there is a morphism, obviously. This morphism is this composition which makes the diagram commute. But GG is the unique morphism whose image under F is this particular morphism. Yeah, that will tell you that. So thus, now we have defined object to object assignment of G and morphism to morphism assignment of G. We still have to show certain other things. What else is there? To show that, to complete the proof that it is a functor. What should we show? Identity. Think about identity. If this D dash was just D and this vertical map was identity, then what will you get? Epsilon D identity, epsilon D inverse. So you will get identity back. So identity is done. What about composition? So G, I should use another color. So uniqueness of GG actually yields functoriality. So here also when we are doing identity, then what we are saying that FGD to FGD there is identity map, namely 1 sub FGD, and that identity map definitely makes this diagram commute. So nothing else can make the diagram commute. So it must be identity itself. Yeah, that's our argument. And similarly, if there is D to D dash and D dash to D double dash and there is a vertical choice, then on the left hand side the vertical choice would be GG, GG dash and their composition. And there will be something else also which corresponds to G dash composed with G, right? So that composition and this composition, they have to agree because one works. So uniqueness of this GG, that yields this functoriality of G. Okay, so this is, you can write this proof down. Yeah, it's simple. So now what do we need to show? The first part we have done. Epsilon is a natural isomorphism. Very good. So epsilon is a natural isomorphism. Is there anything to show here? Epsilon is a natural isomorphism. Is there anything? Why? It was an if and only if condition, correct?
Epsilon D is already an isomorphism.
Correct.
Any object D.
Since epsilon D is an iso for each D, epsilon is a natural isomorphism. Very good. Now, third thing, we have to first come up with some choice of eta and then prove that eta is a natural isomorphism. How do we define eta? Maybe I should write in one that constructing G. Okay, how do we construct eta? So we have to come up with let C be an object of C. We had to figure out a map from C to GFC. Yeah, we need a map C to GFC. Here is a common trick that we use here. Yeah, if composition of two functors in opposite direction is not sufficient, then try to use composition of three functors instead of just two. What do we have? Exactly. Yeah, we already know, we know this morphism FC2 FGFC. We are going to use this trick multiple times throughout the course. Okay. Then what morphism do we know from here to here? FC to FGFC? F of epsilon C inverse. Epsilon C, no. No. Epsilon C, epsilon is only defined for D. Yes. So this is epsilon sub FC inverse. So now observe, yeah, on both sides you have capital F in the beginning. So by fully faithfulness of F, there exists a morphism, unique morphism. Yeah. So since F is fully faithful, define eta C by F of eta C equal to epsilon sub FC inverse. This will definitely do the job. Okay, because we knew one morphism and we can take out F from this. Okay, why does it have two-sided inverses? Eta C should have two-sided inverse.
Eta C should be an isomorphism, so obviously it should have.
Why should it be isomorphism? Is it not possible that a functor takes some non-isomorphism to an isomorphism?
I mean, are you saying we want eta C to be, or I mean, according to this?
No, I'm asking in general. Yeah, is it necessary that if you are given a morphism which is not an isomorphism, then any functor should take it to a non-isomorphism? Is that really necessary? If it is an isomorphism, then the functor should take it to an isomorphism. That is definitely true.
It is necessary because HDF equals to FG.
Correct. Because isomorphism is a property expressed using compositions. So therefore, isomorphism should be preserved. But non-isomorphism should be preserved. Nobody said that. So you can't deduce from just from this expression that f eta c is equal to epsilon fc inverse that eta c is itself an isomorphism. What do you need? F is fully faithful, correct. Because when you do the two-sided compositions of epsilon fc inverse with epsilon fc, then you get identities, and identity is definitely preserved. So since, again, since f is fully faithful, eta c has a two-sided inverse. Okay, I explained all these things orally. And that, oh, we did not check something. We should have, and that eta is a natural isomorphism. Here I am just saying natural transformation, but I just said that eta c is a two-sided inverse for each c. So that will conclude that it is a natural transformation. Epsilon is a natural isomorphism, in that we said that if it is a natural transformation, then it is a natural isomorphism, because each component is an isomorphism. But we did not show that it is actually a natural transformation. How do we get that? Same idea. Yeah, we have actually done that over here. Same diagram. Yeah, while doing that, we have shown that epsilon is a natural. Same diagram, yeah? Yeah, let me just write it, the same diagram, the diagram above also shows that epsilon is a natural transformation. And therefore, it is a natural isomorphism. Similarly, eta is a natural isomorphism. Okay, so this finishes our proof. Even though it's long and it has some interesting ideas, the theorem is essentially very simple. It basically talks about how isomorphism classes of objects are, you just have to choose one object from each class to make sure that two categories are equivalent while preserving the home sets individually. Yes?
How did we show that eta is a natural transformation?
Same argument as fully faithful. You have to, whatever you do for epsilon, you copy it. Yeah. So we are talking about isomorphism classes of objects, right? So let's make those things precise. So some definitions here say that a category C is skeletal if whenever F is an iso in C, then domain of F is equal to codomain of F. A skeletal category is one where there are no non-trivial isomorphisms which are not automorphisms. Okay. Then say that this is the first definition. Second definition, say that a subcategory. Do you understand the meaning of subcategory? That it contains a subclass of objects, it contains a sub collection of morphisms, and it is itself a category. Abelian groups and groups, correct. It is itself a subcat. And abelian groups and groups you mentioned, so therefore there is an inclusion functor, yeah, bit from C dash to C. Now inclusion functor always means, if it is a subcategory, inclusion functor is always faithful. But it doesn't need to be full. Okay, if the inclusion functor of a subcategory is full, then you call it a full subcategory. Okay. Say that a subcategory C dash of C is a skeleton of C if C dash is a full subcategory i.e. the inclusion from C dash to C is full and what should I say?
C prime is skeletal.
Okay, I mean C prime is skeletal, and there is one more property, and every object of C is isomorphic to some object of C prime. Yeah, basically we are asking that the inclusion functor is also essentially surjective, correct. Okay, so so this is a simple enough proposition. Yeah, so given small categories C and D, no, I shouldn't say this, given small categories is irrelevant. Okay, I will say the first part. If C and D are skeletal and C is equivalent to D, then C is isomorphic to D. What is the notion of isomorphism? That there is a bijective correspondence between objects. Yeah, the functor has a two-sided inverse up to equality. Okay, so equivalence between skeletal categories is same as isomorphism, yeah? Nothing surprising over here. And the following are equivalent. Yeah, there are a few properties. This is one. Axiom of choice is equivalent to the fact that each small category has a skeleton. Each small category, even though I am writing small category, is equivalent to any of its skeletons. And last one, any two skeletons of a small category are equivalent to each other. Even though I am talking about small categories over here, I am not really using that the category is small. I am using something weaker, that the collection of isomorphism classes of objects forms a set. Yeah, I am not really using that. There could be however many morphisms. Yeah, that's not playing a role over here.
So locally small works in that.
No, locally small as wouldn't guarantee that the collection of objects up to isomorphism is a set. Yeah? So axiom of choice is equivalent to something, some categorical statement. Okay, so in this particular theorem, yeah, the one about equivalence of categories, what did we see? That there was one important condition on a functor that was just like injective and bijective, injective and surjective. Yeah, faithfulness is injectivity on home sets and fullness is surjectivity on home sets. Now, like if you come back to a single category, then what is the real definition of injective and surjective in a category? Because if you observe, a function is said to be injective if whenever fx is equal to fy, then x is equal to y. This definition uses elements. Can you express this property of injectivity in sets entirely in terms of morphisms? Can you do that? Left and right inverses. Very good. So let me write this definition down. So I am labeling a new part. Monomorphisms and epimorphisms. So this is the first definition. Say that a morphism f from A to B in a category C is a split mono. Mono means monomorphism. If there is G from B to A such that G composed with F is equal to identity on A. If you recall, the definition of isomorphism asked for both. Yeah, G composed with F is identity on A and F composed with G is identity on B. But here we are only asking for one. So this is called a split monomorphism. What will be split epimorphism? If there exists a G such that F composed with G is identity on B. Okay. So split mono and split epi. Now, because I have used some adjective with mono and epi, you can see that this is not the real definition of monomorphism and epimorphism. Because split monos and split epis are very rare in categories. In fact, let's write down examples. Is it true that every morphism is, every injective function is a split mono in the category of sets? Yeah, injective if and only if split mono. And is it true that surjective if and only if split epi? Using the axiom of choice. Very good. So this is actually equivalent. Like which direction is obviously clear?
Split injective implies split mono.
Yeah, the first one doesn't, but I'm asking surjective implies split epi is clear or split epi implies surjective is clear? Split epi, right. Very good. Okay. Converse is true here if and only if axiom of choice holds. Okay, otherwise it doesn't hold. In general, okay, in many categories that are of interest to us, monos are well behaved, but APs are not. Epimorphisms always create problems, even though it seems that they are just dual conditions. Yeah, because you can see that a split mono in category C is just split epi in category C op, and vice versa. But still, epimorphisms are usually harder to understand. Okay, so let's write down the actual definition of a function, injective function. Yeah, this is just some discussion. What do we say? A function f from a to b is injective if for all a prime in A, fa equal to fa prime implies A is equal to A prime. Yeah, this is our definition, simple definition. But we have also seen what is the meaning of an element. Can you express an element as a morphism in the category of sets? Huh? Singleton. And what is singleton? What is the role of singleton in the category of sets? No, singleton is not the initial object, it's the terminal object. Correct. So, terminal object to this. But terminal object is not really important. Okay. So, basically A and A prime, if you think, so actually this is what is happening. A and A prime are the names of these morphisms, and then there is F. And we are claiming that whenever Fa is equal to Fa prime, then A is equal to A prime. Now this is the actual definition of a monomorphism, but we are going to generalize it and not worry about a terminal, because terminal may not exist. For example, in the category of rings, unital rings and 0 not equal to 1, there is no terminal object. So therefore, let me define it. So say that a morphism f from A to B is a mono if whenever C whenever fh is equal to fg, then h is equal to g. Okay, this condition should hold. You notice that we have just changed one to any object. Yeah, so actually if you look at this h or g, then in category theory language we call it a generalized element. Okay, so G is a C element of A. Okay, we are treating every object and every morphism as an element. Okay, so H is equal to G. So this is our definition. What will be the definition of epimorphism? You can write it down, yeah. So which property is this? Left cancellativity or right cancellativity? Left cancellativity. If you all say so, okay, my left and right is bad. So this is left cancellation and right cancellation is epi. Right. So is it true that a morphism in sets, example, yeah, I mean, oh yeah, I should say something. So the notation is that this is the notation. This is a monomorphism, F from A to B. And dually, yeah, this is a mono. And dually, F from A to B, this is an epimorphism, yeah, with double arrow. Maybe I should also, before starting with examples, say that F from A to B is a bimorphism if it is both mono and epi. Yeah, bimorphism. Now you might be wondering, why am I mentioning this, like mono and epi? Shouldn't it directly give you isomorphism? Because that's what our intuition says, yeah? Injective plus surjective is bijection, and bijective means iso. But not every time bijection is an isomorphism. So a category, say that a category C is balanced if each bimorphism in C is an iso. Okay, so some categories are balanced, some categories may not be. So now we are ready to look at some examples. Oh, I mean, okay, even before examples, what is the connection between monos and split monos? Let me show you the definitions again. Are all monos split monos or split monos are monos?
Split monos implies mono.
Split mono implies mono. Why?
Because if you have H equals Fg, then you can take the left inversion.
Correct.
You get H equals G.
Yeah. So if you have Fh is equal to Fg, then you compose it, post compose it with the left inverse for one-sided inverse for F. Yeah. And then you will get H is equal to G. Yeah, because I'm calling it F prime. Yeah, so from here you can conclude that F prime Fh is equal to F prime Fg, and F prime F is identity, so identity composed with H is H follows from axioms of category. Yeah. So this is so this is the proof for, yeah, if F is split mono, then mono. So split mono is actually a strong property. It's actually very strong. So strong that it's also preserved by every functor. Yeah. every functor will preserve split monomorphisms and split epimorphisms. Actually, monomorphisms and epimorphisms in different categories, you need different types. So right now you have seen two different things, yeah? But there are also regular monomorphisms and regular epimorphisms. Then strong monomorphism, strong epimorphism. So there is a wide variety of such things, and we will encounter these things as we progress in the course. And then interrelations between them. So they are all interesting topics. So now actually we can talk about examples. The first one in the category of sets. So the question is every injective morphism a monomorphism? Yes, because injective is split mono and split mono is mono. So injective implies mono. What about the converse? Is every monomorphism an injective morphism? No? No, what about this? This diagram was constructed, look here, yeah? This particular diagram was constructed only for that. If it is a monomorphism, then for every choice of C and every F and G, whenever the compositions are equal, then G is equal to H, correct. So in particular, I can choose capital C to be equal to 1 and H and G to be 2 elements. So it will boil down to the definition of injectivity of the function. So therefore, I have explained to you that monomorphism and injective morphisms are exactly the same. If you remember, a similar statement for split monos was also true. Injective if and only if split mono, if and only if mono. But in surjective if and only if split mono in category of sets, that wasn't true. That was, one side was always true, but the second side was true subject to axiom of choice. However, for this notion of an epimorphism, we do not need that. So here I'm saying, so surjective morphism, is it a split mono or not? Split epi, sorry. Is surjective split epi? Yes, so split epi implies surjective, that is clear. Okay, so we don't have that. But can you show that surjective morphisms are epimorphisms?
Yes, sir. We can show that.
Yes, how?
We can take a set containing 2 elements and then I mean.
Okay, good. So set containing 2 elements. I'm just going to write this down, yeah. So I'm going to say this is a morphism G, and you are going to take a set containing 2 elements. And which 2 functions are you going to consider here?
I mean, so we will towards the contradiction assume that G is not surjective. So
It doesn't matter, like that we'll see later, which 2 functions.
so I mean we can 2 functions. So
We'll need 2 different functions, which may not be always the same.
One is image of A, image of G.
Image of G is
One.
a set. You have to convert it into a function. You are on the right track.
image of G map to one of the elements and then rest of them to other.
So that's called a characteristic function. Okay, so I'm going to write characteristic function of image of G as one function. And what is the other function? Constant function. So characteristic function, we are going to take value 1 if the property is true, otherwise 0. Yeah, so this is 0, 1. And this one I'm going to just choose 1. Yeah, constant 1 function. Okay, so if G is an epimorphism, then this diagram, like 1 composed with G and chi im G composed with G are equal. Yeah, so let me write this. If G is epi, then 1 composed with G equal to chi im G composed with G, that will imply what?
One equals chi image of G.
And what does that mean?
Image of G equals B.
Image of G is equal to B, which means G is surjective. So you still haven't answered my original question. So we proved the reverse implication. So epimorphism is a surjection.
So we know axiom of choice is equivalent to retract property.
But that was split mono. But we don't want to do that.
I mean, for surjective, we can just show by like.
We can just show.
Yeah, we can directly show.
Okay, let's try to show that. So if G is surjective, what can you say?
We can say if G is not surjective.
If G is surjective, then what can we say? Suppose you are given a diagram. Yeah, A, G, B, C, and I am calling this H and K. Given this with Hg is equal to Kg, what can you conclude?
H equals K.
No, whenever this is given, what do you know?
We know that H restricted to image of G equals K restricted.
No, then you just write it down. Yeah, H of G of X is equal to K of G of X for all X in A. Since each element Y of B is of the form G of X for some X, what did we conclude? H of Y is equal to K of Y for all Y in B, and therefore H is equal to K. This is the definition of equality of two functions. Done. So actually this is if and only if. And the conclusion is that because we know that injective and surjective together imply bijective, and bijective if and only if isomorphism. So therefore sets is balanced. Okay, I'm just going to continue writing over here. Second example. Yeah. In the category of groups, I think we are using GR. In GR, mono if and only if injective, yeah, and AP if and only if surjective, both hold, and GR is balanced this also holds, but there is one catch here, that the proof that we used here, yeah, this proof which used the element 2, I mean the set 2 element set. Now that 2 element set we can't use in the case of groups, because 2 element group has very specific properties, so you don't want to do that. So the proof in fact uses something different. So which part was that? Epi implies surjective or surjective implies epi? Epi implies surjective. So epi implies surjective was shown by Schreier, Niels Schreier. He's the same person, if I remember correctly, who proved that every subgroup of a free group is free. Every subgroup of a finitely generated free group is free. So this property was shown by Schreier using free products of groups and amalgamations. Yeah, you have seen these things in algebraic topology, Van Kampen theorem. Yeah, so those things. So you can see that even writing down a very simple statement, epimorphism is surjective, that's not easy. Later on, several people have given other proofs. There is also a single page proof of this result. But all of those proofs need some knowledge of group theory. Yeah, it's not easy. In rings, okay, in the category of rings, I am just going to talk about this particular map, which is Z to Q. This inclusion. This inclusion is because it's, so if you see, then monomorphism, injective function is a monomorphism. That argument doesn't really depend on anything as long as you have a concrete category that argument goes through. Yeah, or epimorphisms are, surjective morphisms are epimorphisms. That thing also generally goes through if you have a concrete category, even though I haven't defined what is concrete. If the objects are sets and the home sets are also sets, then we call it a concrete category. Then that proof will go through. Maybe I should write it afterwards. Home sets contain functions, yes. So you want me to write it, I will do it immediately. So this is the definition. Say that a locally small category C is concrete if there is a faithful functor U from C to sets. I couldn't do it earlier because I had not defined faithful. So the category of groups is faithful, category of rings is faithful. Why is it faithful? Because every single group homomorphism is a function to begin with. Every group is a set and every group homomorphism is a function. Every ring is a set and every ring homomorphism is a function. And you can distinguish between two different group homomorphisms by looking at their underlying functions. Yeah. So this is, so I mean, for example, any category of algebras, that is a concrete category. Yeah. So sets, a category of groups, abelian groups, rings, top, yeah, all of them are concrete categories. But there is a paper which says homotopy is not concrete. Yeah, this is the title of a paper, I think by Peter Fried or Peter May, one of those two. Yeah, I will confirm it next time.
So what is the homotopy category as the object?
So HTPY, yeah, this is not concrete. The category of homotopy equivalences of spaces. Yeah, that's not concrete. Okay, now let's come back to this original thing that we were doing. This particular morphism Z to Q, it is injective, so therefore it is a monomorphism, but in addition it is also an epimorphism. Is a bimorphism, but not an iso. Obviously it's not an isomorphism. Why is it a bimorphism? Why is it an epimorphism in particular? If you are given, yeah, let's consider this. So Z included inside Q, and now you have got two morphisms, let me call them F and G, to some ring R, such that F of n is equal to G of n for all n in Z. Then can you conclude that F of P by Q is equal to G of P by Q?
Yes, sir.
How?
Because it is like f of p into f of q inverse, and I mean
F of Q inverse.
I mean
F of Q inverse is not the right idea, but F of P by Q added to itself Q many times is going to be F of P, and where it happens. So this is a divisible situation. Yeah. So therefore this happens. Yeah. So you can you can show that F of R is equal to G of R for all R in Q.
we can talk about f of q inverse, right? Because
It's a multiplicative inverse.
like this.
Yes, but the reason is slightly different here. Yeah, because you are using addition repeatedly. No, I think multiplicative inverse will also work. Yeah, the fact is that, yes, okay. The fact is that Q is a localization of Z, and that's why it works. Yeah, so any integral domain to its field of fractions, that inclusion is going to be a bimorphism. Any localization map is also going to be a bimorphism. You understand localization? If you are given a ring R, let's say commutative ring R, and S is a subset, multiplicative subset of R, then R to RS inverse, there is a natural map, and that natural map is always a bimorphism but not an isomorphism. Yeah, so therefore rings is not balanced. Can you tell me whether top is balanced or not? No? Tell me why.
And we have seen bijective continuous functions.
Bijective continuous functions which are not homeomorphisms. So tell me what?
I mean, we just have to check that injective continuous functions are mono and surjective continuous functions are epi. If it happens, then it is not balanced.
So give me one example. When you are saying it's not balanced, then give me an example.
Zero R equals to x cube.
R to R. Which continuous function R to R?
X to x cube.
X to x cube. You have another example?
Close 0,
R goes to the circle.
close 0, open 1 to circle.
This is better. Yeah, R goes to the circle is, yeah, you can do that as well.
Wrap it many times.
Huh?
You can
Wrap it many times, but we want some bijection also. Yeah, so this mapping to S1. x mapping to e to the 2 pi I x. This map is bijective, continuous, but its inverse is not continuous. And therefore, top is not balanced. Yeah, so therefore not a homeomorphism. Homeomorphism is a stronger condition than bijective continuous function. And homeomorphism means an isomorphism in the category of topological spaces. Okay, so yeah, I mean, you have seen several examples of categories. You should try to figure out what are the monomorphisms and epimorphisms in all those examples. Yeah, and let's stop here.